All right, a few words on universal expansion. Based on what we had talked about before, we use Hubble's law together with those deep images like the Hubble Deep Field. And what we do is we look at sort of a strip of sky and all the galaxies you can see on a strip of sky. Then we can pinpoint how far away each of those are. And what we get out of that is something that looks like this. It's sort of a pie slice. We're here all the way across is our strip of sky. And what we do is we get these distances, so we're looking back into the universe when we do this. And what we see is this large-scale structure, which is the same everywhere. We're going to say that that is the same as homogeneous, and it's the same pattern in every direction. And we're going to call this isotropic. These are words that don't come up very often in casual conversation. In fact, let me fix this. It's the same everywhere is not quite the right thing to say. Same every place. So what I'm saying is every patch of sky looks like this. And what do I mean by this? What we see are these voids, and then we see these filaments of galaxies. These are called superclusters. And the universe seems to be arranged in patterns of voids and filaments. Really, I mean, it really just sort of looks like the inside of a sponge. So that if you just took a sponge and dipped it in paint, there's some home decor fad, right? Where you sponge paint the walls. And it looks something like this. You just dip your sponge in paint, put it against a wall, and you get this kind of a pattern. This is what the universe looks like on really large scales. So each of these dots in these representations, each dot represents a galaxy or a cluster of galaxies. And each one of those, remember, has like hundreds of billions of stars in it. So this is a huge slice across the universe. And what we see is on really, really large scales, the universe looks like this. It looks like the inside of a sponge, voids and filaments. This pattern, the size of the voids and the size of the filaments, really looks the same on every scale. If we scale way up, if we look deeper into the universe, we don't discover anything new. Well, except for new voids and filaments. What I'm saying is they're always the same pattern, always the same size. Sort of like a carpet, where some abstract piece of carpet might look the same, right? You would say one patch of carpet looks like any other patch of carpet, even though if you drill down, I mean, some little fibers of carpet might look different from each other, but the overall pattern looks the same. So on really large scales, we say that the pattern of the universe looks homogeneous. It's the same patch. Another way to put it is, if you took a jigsaw puzzle of the universe, it would be really, really hard to put it together because you don't get any clue about where you are from what the pieces look like. Every piece has the same pattern as every other piece. So that's called homogeneous. That's this word. And the other word is that we get the same pattern, not just at every place in the universe, but in every direction. So we call that isotropic. Every direction we look, we see the same number of voids and filaments if we look out in any particular direction. That still might be confusing. Let me say it like this. Suppose you have a field of wheat, like an infinite field of wheat, and there's like a wind blowing from one side to the other. So the wheat is sort of blown over. Right, the stalks are all sort of blown over in one direction. Okay, I mean, again, imagine this is like infinite. So imagine you're taking a picture from a helicopter, hovering over this field. Is this field homogeneous from place to place? I'm going to say yes, because if you take a photograph of this field at any place, it looks like the field from any other place. So a jigsaw puzzle, you would have a hard time putting together a jigsaw puzzle field like this because there's no clue as to where you are. Every piece looks like every other piece. So this looks like homogeneous. Yes. But is it isotropic? Okay, here's the distinction. So if I were put in here, if I were in the middle of this field, would the field look the same in every direction? That's the crucial thing. And I'm saying no, because if I look this way, all the grain or all the stalks are bent towards me. And if I look this way, all the stalks are bent away from me. So it does not look the same in every direction. So is this isotropic? Nope. Because I can tell a direction. That's another way of saying something is or isn't isotropic. It's not symmetric over the circle around me. I can tell a preferred direction, left or right, by whether the stalks are bent towards me or away from me. So this is an example of something that is homogeneous but not isotropic. Can I imagine something that is the reverse? Something that looks the same in every direction but is not the same place to place? Well, maybe it would be something like this. Maybe I can make nicer circles. Something like this. And that. Here's an example of something that if I were at the center and I'm looking out in every direction, it's symmetric, right? So this one is isotropic. It looks the same in every direction. I get a boundary of the red circle, and then I get a boundary of the white circle at the same distance. So it looks symmetric in every direction. It looks isotropic. Is it homogeneous on this scale? Not really, because if I took a picture here and took a picture here and took a picture here, I could tell where I am just by looking at the pictures. That would be a pretty easy jigsaw puzzle to put together. On this scale, it is not homogeneous. It's not the same place to place, but it is the same pattern in every direction. Okay, so those are two quick examples just to kind of, because I think the book uses these words homogeneous and isotropic, and the book isn't real clear about distinguishing those two. So that's a way that you can distinguish them. But anyway, that the universe is homogeneous and isotropic is called the cosmological principle. The universe is homogeneous and isotropic on large scales. So that the universe is both of those things is called the cosmological principle. So it basically just says that everyone in the universe sees the same patterns. By the way, notice what that means. Look at what this implies. And we'll see if we can get this to make more sense, but I'm just going to put this out there. If something is homogeneous and isotropic, that means everyone sees the same pattern, right? Look what this means. This means that there's no edge to the universe. Because what if there was? If there was an edge, then imagine someone right out close to the edge. They look off in one direction and they would see like the universe. Then they look in the other direction and they would see, if they're at the edge, and they would look off in the other direction and they would see like whatever that would be, no universe or whatever. I don't know. I can't imagine it. But anyway, it would look different. If you're on the edge, it would look different one direction than another, right? So it wouldn't be isotropic. So this condition that the universe is homogeneous and isotropic for everyone implies that there's no edge. And if there's no edge, guess what that means? There's no center. How are you going to have a center if there's no edge? Because how do you define the center? The center is the same distance away from the edges. So if there's no edges, there's no center. No one can say that they're the center. Or everyone can say that they're the center. Okay, we'll come back to this, but I'm just putting this out there. That this is a powerful statement if the universe obeys the cosmological principle, if it's homogeneous and isotropic, there's no edge, no center. Okay, neat. So apparently this is what the universe looks like at large scales. Oh, by the way, I wanted to just say, it looks like all the galaxies sort of peter out at large distances, like there's not as much stuff way out here as there is close in. It looks brighter, right? More galaxies closer in. That's just called an observational bias. It kind of makes sense if you think about it. Why would there not be many galaxies observed further away? It's just because we're not seeing the dim ones. The ones that are in here close, we can see the dim ones because they're closer. So we count more galaxies. The ones that are out here, we're only sampling the brightest ones. We're not seeing the dim ones, so it just looks like there are fewer galaxies. But when you correct for that, it turns out they're the same number of galaxies. That's why the pattern looks the same. So that might be an objection. You're looking at the diagram saying, wait a minute, it looks different far away than close. It looks like there are fewer galaxies. It turns out there really aren't. It's just because we only see the bright one. So we can correct for that. Okay, so how does this work? How can everyone, remember how the Hubble expansion works? Hubble's law says that not only are all the galaxies expanding away from us, but the ones that are farther are moving faster, which is a very kind of a strange thing. I'm having you go through a lab to kind of bring this point home this week. Here's the idea. I won't work it out in detail, but here's the idea. Imagine you have a rubber band, and imagine there are ants on the rubber band or dots on the rubber band. And you can label them like this. And then suppose you stretch the rubber band. And the way the rubber bands work is when you stretch them out, let's suppose this is the wall. I think I might have it slightly different on the assignment, but whatever. So anyway, here's the idea. That when you stretch this thing out, proportionally, the distance between all these things stays the same, but they do kind of expand away from each other, right? What you're going to show in the lab is the distance between A and B has gotten larger in a certain amount of time, and so you can calculate the speed. So if you're ant A, you would say, ant B is moving away from me at such and such a speed because the distance between you has grown. And look at C. Look, it's even plain just from drawing just a rough little diagram. C has moved farther away than B did. So C is moving away faster. And look at D. D moved even faster, right? So this kind of stretch is what we're really talking about. Hubble's law really implies a stretch, so that now it makes sense. If the universe is stretching like a rubber band, it makes sense that the things that are farther away are moving away the fastest, because that's just the way that elastic materials work, rubber bands or whatever. If space is stretchy, this is the way it works. A uniform expansion is a stretch. And so viewed this way, it's really not so surprising that things that are far away are moving the fastest, because that's just the way it works. That's the way uniform expansions work. Here's another thing that you can probably get from your lab whenever you go through the little calculation, is that if you're ant A, you would for sure, I have you carry through the calculation for A, you would say, yep, B is moving away from me, C is moving away from me even faster, D is moving away from me even faster in proportion to their distance. So that's the Hubble law. What you can satisfy yourself is with, anyway, you can satisfy yourself of the following thing. If you're ant B, what do you see? You see the exact same thing. You see every dot moving away from you. So here's a big point. Every dot sees the same expansion. If you're ant B, you see everyone moving away from you the farther the faster. If you're ant C, you see exactly the same thing. If you're ant D, you see exactly the same thing. So every ant would think that they're at the center, right? Every ant would say, oh, all you guys are running away from me, the farther ones are moving away the fastest. So every ant would think, if they didn't know any better, they would think that they're at the center of the expansion. But it turns out that a uniform expansion means that every dot sees exactly the same thing. Aha, that's towards the cosmological principle, right? That supports it. So every dot sees the same expansion. How about this? This is also true. The dots aren't moving on the band. That's true also, right? They're moving away from each other, but why? It's not because the dots are moving on the rubber band. So in the analogy, what I'm saying is, it's not that galaxies are moving through space, but the galaxies are being carried away from each other by the expansion of space. There is, in some sense, more space being created between the galaxies. Just like there's sort of, in some sense, more rubber band that's being created between the dots. The dots aren't moving on the rubber band, the dots are staying fixed, but they're being carried along by the expansion of the thing that they're in, the rubber band. So what we say is that the galaxies are being carried along by the expansion of space itself. Now you have to imagine that space is like a stretchy fabric, which apparently it is, according to Einstein. And so galaxies are carried along by the expansion of space itself, which is kind of... So the dots aren't moving on the band, but they're being carried by the expansion. Very cool. And no two... This kind of goes along with the first one. No two dots are approaching each other. Right? Every dot is moving away from every other. You might say, wait a minute, what about like the Andromeda Galaxy? What about in our local group? Well, that would be like two ants that are initially really, really close together, and when you stretch the rubber band, they would separate from each other a little bit, but their little motions are faster than the speed with which they're carried along by the rubber band. So all I'm saying is, if galaxies are really close to each other, like in local groups and clusters, their motions inside the clusters could overwhelm the expansion of space. That's only really important on a large scale. So now if you imagine that A, B, C, and D are not individual ants, but maybe they're little ant colonies. So this is a very, very large rubber band. So if those are ant colonies, it sure could be true that within ant colony A, two ants could be approaching each other just because they walk faster than they're being carried apart. But individual colonies, in other words, the clusters themselves, are being pulled further apart. Okay, this is the one-dimensional example, just dots on a line. And we're trying to use this as a kind of a metaphor for how the universe is expanding. But we've reached kind of the end of the usefulness of this metaphor, this analogy. All analogies break down eventually. We just use them as long as they're useful. So here's another one. Instead of a one-dimensional rubber band, have you ever seen a two-dimensional rubber band? The answer is yes. Everyone has seen a two-dimensional rubber band because a two-dimensional rubber band is called a balloon. So all we're going to talk about is just the surface of the balloon. No fair talking about what's inside the balloon or off the surface of the balloon. So just on the surface of the balloon, the thing that an ant crawling on the balloon would see would be something like this. What we say is, at early times in the universe, we have a small balloon. And then over time, the balloon expands. Let me see if I can match the dots. So we get the same pattern of dots in the early universe and now. So the pattern doesn't change, it just gets spread apart. That's the idea. This is a two-dimensional rubber band. The mathematics is harder to prove. The one-dimensional case is pretty easy. The two-dimensional case follows from the one-dimensional case. It's harder to prove it, but it still should make sense that that the bullet points still apply. If you put dots on a balloon and you blow the balloon up, no two dots approach each other, right? They all get further apart from each other. It turns out that the Hubble's law still works on the surface of a balloon. The dots that are farther away from each other are moving apart faster as it expands. So they would still see the same Hubble's law, but now it's a little bit more clear that every dot thinks that it's at the center, right? There's no edge to the surface of a balloon, right? Because an ant can just keep walking and walking and walking and never fall off. So if there's no edge on the surface of the balloon, there's no center either. There's no center point on the surface of the balloon. Again, no fair going down into the center, but there's no center on the surface. So every dot has a claim to being at the center. And if every dot thinks that they're at the center, guess what? No center, right? It's not even a well-defined concept. Some things, if you ask, where's the center on the surface of a balloon, the question itself is just ill-defined. It just doesn't make any sense. You can't answer it. It's like saying what's north of the North Pole, right? There are some things that are just not defined. So in this sense, this is a closer analogy to the real thing. So now you can kind of understand, you can get in your head that there is such a thing, such a surface that has no center and no edge. It's like the surface of a balloon. And all these dots expand away from each other. Very cool. So what we're going to do next time is, now we'll talk about how light travels from the early universe to now, and how we can have things called horizons, and what it means to trace the expansion backwards in time. I mean, here's the short, sort of the spoiler alert. If this is now, what happens? And now, the universe is filled with radiation. It's filled with light. It's filled with gas and stars and so on. Well, what happens if you make it smaller? If you go back into the past and you make the universe smaller, well, what happens if you compress a gas or you compress radiation? Turns out you heat it. So what you might suppose is that if we run the clock backwards and we go further into the past, the universe gets hotter. Which is true. If the universe gets hotter and more dense, if we just run the clock all the way back, we get to a point eventually where the universe was so hot and dense that fusion could have taken place, right? The entire universe could have been an extremely hot, dense state. And we call this idea Big Bang, because then you run it forwards and it's almost like an explosion. Okay, so that's where we're going with this, is that once we realize this motion of galaxies is really more like a stretch, then it doesn't take long before people start running the clock backwards and try to learn what happened in the very early universe. So that's where we're headed.